Hello, this is the next video in my playlist, General Linear Models 1. And we're going to look at the properties of the least squares estimates of our simple linear regression line. So in the first few videos, we kind of gave some intuition for simple linear regression. We derived the least squares estimates, and now we're going to give properties of these least squares estimators. Here, this is the line, yi equal beta naught plus beta 1 xi epsilon. This was the error term. More details are in the videos just before this video of our line here. Then we derived least squares estimates for our beta parameters, and they were this. So where the SXY is this sum and the SXX it was this sum. Least squares estimate for beta naught hat was y bar minus beta 1 hat x bar. And the y with a hat on it, that's our fitted line. So we have data that if you plot it, and then the line that best fits it according to least squares criteria is what we call y hat. So let's jump right in. First of all, let's show that beta 1 hat and beta naught hat can be written as these estimates. So the parameter of interest times, plus this sum, parameter of interest plus this sum. And this is going to help us when we calculate its expected value and the variance and covariance and stuff. And so where di is this quantity here, xi minus x bar over xxx times the error term. So the proof, let's do beta 1 hat first. It is SXY over SX. And this sum is this term. Now this isn't indexed by that, but we can still bring it in. And then YI is this line, right? So we're substituted in for that. Oh, we don't bring that in just yet, sorry. And then this is it. Now, we multiply this quantity into each term, right? And then when we look at this sum here, in a previous video I showed how this sum goes to 0. And now let's look at this sum, which is here, and then we multiply that x into it, and then we take the sum in and we get this. But this is sum of the xi's you can think of as n times, divide by n, multiply n, so you get x bar squared. Well, this is actually part of the variance formula, or SSX, so that is this piece is xxx. Now it simplifies to this. So this sum goes to 0, so it goes away. This is SXX, but divided by SXX leaves beta 1. And then here, when we bring this and divide it by that is what we were calling DI, and that's times epsilon I. So that is equal to this. Now, for beta 0 hat or beta naught hat, it was defined like this. Now, the y bar is the sum of the yi divided by n. So we replace the sum of the yi, but we replace yi by this line and divided by n. This over here, we replace beta 1 hat by what we just derived. Then over here, we take this sum in, and beta naught over n summed from 1 to n is just beta 0, beta naught. This, the sum that comes in and we get beta 1 x bar. And here it's the sum of the epsilon over n. We'll just call that epsilon bar. It's the average error term. This right here comes in, we get this, and then times this sum. It's not indexed by it, so we can bring it out. This and this term cancel, this comes down, the error term, and this. And this is what we wanted to show, that beta naught can be written like this. Now it's going to play a big part in what we do in the next couple of pages. So let's show that our least squares estimates are unbiased. That means the expected value is the parameter that we're interested in or that we're estimating. So let's prove that. So the proof that beta not hat is unbiased. So we plug in what we know about beta not hat, what we just derived, right, is this. Now the expected value comes in, and expected value of a constant, just a constant. And this is the sum of the epsilon over n, and so that expected value goes in and becomes this. And then here, d is a constant because it's of the x's. And so when we take the expected value into this, that's constant, this constant, so it just goes straight to this epsilon term. Well, the standard assumption 1 is that these error terms are 0, or the expected value of these error terms are 0. So that drops out, and we're left with just beta not. So it is unbiased. Now beta 1, the expected value of beta 1, we plug in what we derived in property 1, and the expected value of constant is just a constant. Expected value here, the di's are constant, so it goes in and then goes in, and it's just on the epsilon I. But this is 0 according to standard assumption 1, and so it's beta 1. And so that is unbiased. So now let's find the variances of beta, our least squares estimates of beta not hat and beta 1 hat. And we get this. So beta not hat, we plug in property 1 for beta not hat, and it becomes this. Beta not's a constant, so that doesn't factor into a variance, so that can be dropped out. Here we're going to write this as the sum of the epsilon divided by n, and we'll keep this the same. So that's what we get here. Now, for this term, they're both summed from 1 to n, so we can bring it into one sum, and there's an epsilon constant, so we can factor that out, and that's what we do here. Now, the variance goes into each term, but then you also, these are constants, so we're looking at the variance of the epsilon i's. And so normally there'd be a covariance between the epsilon I and say epsilon j in this sum, but a standard assumption 3 is that the covariance are 0. So that there's no covariance term in this variance. So we bring in the variance, and then we have to bring out the constant term squared, and then the variance of this inner piece. Well, this variance of that's sigma squared, so that comes out of the sum, and we're left with this. So when we square it, we get 1 over n squared, 2 times this sum, and then this squared. Now we bring in the sum into each of these pieces. So this becomes 1 over n. The sum goes straight to the di, the sum of the di, and then the sum of the di squared. Well, the sum of the di is 0, and I'll let you do that on your own. But here for the sum of the di squared, and actually we did something very similar in the second video in this playlist showing that 0. This is this right here, it's a note. So di was xi minus x bar over sxx, and we're squaring it. So then that squared term can come out of the index, and then it's this squared. But this sum is what we're calling sxx. So you got sxx over sxx squared. So one of those canceling, we're left with 1 over x. So this piece is still there. This piece goes to 0 because of the sum of the di. And then this is going to be x bar over sxx. And that's what we get. And so that's the variance of beta not. So let's find the variance of beta 1 hat. So we plug in the property from property number 1, and this constant doesn't factor into the variance, and so it's the variance of this sum, but the random term is this epsilon I, so the covariance between, say epsilon I and epsilon j are 0, so there's no covariance in here. So when it comes in, the variance of this, the di comes out front because it's constants vary this, and that's sigma squared. So it comes out of this sum, and the sum of the di squared, we said, was 1 over sxx. So that's the variance of x1 bar. Now we want to show that our least squares estimates are linear in the y's, and this is going to play a part later in this series, because when they're linear in the y's and the y's are independent normal random variables, then these are going to have some nice properties. So we want to show that they're linear. So beta 1 hat is defined like this. That's the least squares estimate. This numerator is this sum right here. Now we want to bring this into the sum. Remember, I kind of mistakenly said that earlier. So we bring it in, and that y is here. So this is these are constants. So it's the sum of a constant times yi, and that's what this is. So a is this, and this is how we define linear estimators in video number 1. So video 2, so beta 1 is a linear in the y's. So beta 1 hat is this. Well, this is the sum of the yi's divided by n. Beta 1 hat we just showed was this. So that's this piece, and the x bar is here. Now, the sum from 1 to n, we can make that one sum and then factor out a yi, and that's what we do here. So the 1 over n's come down, this comes down. So it ends up being a sum of a constant times the data, yi. So we can think of it as, say, the sum of ki yi, and so then that proves that it's linear in the y's. Now the covariance, ultimately I want to do the covariance between beta naught hat and beta 1 hat. But this is an intermediate step before we get to that point. Now, so let's look at the covariance of y hat and beta 1 hat. And so we plug in what we know about y bar. And that really, let me flash that. So our least squares estimate of beta naught hat is this. So if we add this to the other side, then we get y bar is equal to that. And that's what I put here. So now the covariance is, you take the covariance of this and the covariance of that. So that's what this piece is. And then the x bar comes out, and the covariance of beta 1 hat and beta 1 hat is really just the variance. So we write that. Now beta naught hat was this right here from property 1. Beta 1 hat was this, and of course this comes down. Now the constants don't play a part of covariance, so we can get rid of them. And then in here, when we were doing the variance of beta 1 hat, we showed how that this is the sum of the epsilon I over n, and this is, ends up being the same sum. We can combine them, and we factored it into this. So that piece is this. And then this is just the sum of, it comes down, and then this piece comes down. So now, but one note here. Here in this step, I have the index is I, and the index is I. But that's really could be anything. In this step, I emphasized that I made this a J and this an I, because they should be different for clarity. And so when we do this covariance of all these sums, really we're indexing it over J and I, so that when we bring this covariance into that double sum, then it's the covariance of this, and then since those are constants, they can come out front, and we're just left with the covariance of these. But standard assumption number 3 says the covariance of any two F's, or the air terms, are 0. So whenever I and J are not equal, this is 0 and it doesn't contribute to that sum. So really we can think of that as one sum, just from I equals 1 to n, of this sum. And of course the covariance of epsilon I and epsilon I is the variance. And then of course these terms come down. This is sigma squared, which can be factored out of that sum. And then here we have the sum of di's, right? Because we're bringing that sum in, and then this sum is here. Well, the sum of di from 1 to n is 0, so that goes away. And we said the sum of the di squared from 1 to n is 1 over sxx. So this piece, so then when we bring this in, that's this piece, and that piece is here, but it's the same thing. We're adding it and subtracting it, so it's 0. So the covariance of y bar and beta 1 is 0. Now, so let's find the covariance between our beta parameters. And so it's this, and then the beta naught hat was this. That's our estimate, our least squares estimate. So when we find this covariance, we take it, the covariance of this times the first term, and then these two terms, and that's what we do here. And x bar is a constant, so it comes out front. And then we just showed that the covariance of y bar and beta 1 hat is 0, so that goes away. The variance of beta 1 hat was x bar over sxx, and so this is it. So this is the covariance and of our terms. Now the next two properties, and this is the last property, we're on page 4. It talks about our data, which is yi, and the fitted line. Now remember the fitted line, yi hat. The hat means that this is now the line. So this is beta 1 hat plus beta naught hat plus beta 1 hat xi. So it's the line. So if we plot it, that line going through there is this, and that's the actual data. And so this sum is 0, and we're going to show that this sum is 0. So here, so we plug in what we know for yi bar, which is this. So that's our fitted line. Then we plug in what we know about beta naught hat, which was y bar minus beta 1 hat, but that minus kind of reverses that. And then here we get minus beta 1 hat x bar. Well, so then we take the sum in, and we get the sum of so we think of it in two terms. This sum, so it's 1 to n of yi minus y bar, and actually that's what's over here, right? And then we take the sum into this, and it's not indexed, so we get n of those. So it's n beta 1 x bar. And then here the sum goes into this, so we get beta 1 hat, the sum of the xi. So if we divide by n and multiply by n, then we get minus n beta 1 hat x bar. So those two cancel. And that's why we're just left with this. And then this can be easily shown that it's 0, right? So this is the sum of the yi, and this would be the sum of your minus sum of y bar. But that's not indexed, so it's going to be n of those. So n times y bar is the sum of the yi over n, so the n's cancel, and we're left with, the sum of the y minus the sum of y, which is 0. Now this here, we're going to prove this term here. We plug in our fitted line, which is this. Then we multiply this x into the terms. So that's what we get here. So this is this term, and then the xi comes in, and then that comes in here. But it looks like I also took the sum into both of those, or all three of them. So that's what we get here. That's this term, and then beta, the squared is this, but it's the sum. Now, this comes down, and over here, beta naught hat, we replace by what it is, the least squares estimate, y bar minus beta 1 hat x bar, and then we got the sum of the yi's, but I divide by n and multiply by n, that's what this is. Now over here we just leave it the same. Now here we leave the same, and then we, I multiply this into here, which is what this is. All right. Now this term, this times that, and this, we factor out a beta 1 hat. Right. So then we're left with this right here. So the minus, that's where the sum of the xi squared comes in. And then This over here is this piece. It's in x bar squared, right? And so see, the minus and minus make that a plus, and then when you multiply this times that, that minus becomes a plus. Anyway, so that's it. Now here what we do is so this is what do we do here? Oh, there's two terms. So this right here becomes this piece. So if we let one of the ends, this end cancel with the y, the sum of the yi over n, so that end cancels this end, then we get another sum from one to n of the xi's. So we can combine that sum and then factor out a yi, right? And that is this, and the x bar stays this. So this piece is this piece right here. Now this, the least squares estimate is sxy over sxx, and then this sum right here we showed earlier that it's sxx. So those cancel, and we're left with sxy, which is this piece, you know, the minus. But this is actually the definition of xy, and so that difference is 0. So this sum is 0. All right, well, that's all I had for today. It got a little long. The next video, I want to show how to estimate the variance of the error term. And specifically, the standard assumption number 2 is that the variance of our error term is sigma squared, and I want to estimate that. And that's the next video. Well, I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.